Okay, so let me start my second talk. So I have been talking about some rigorous simulation, but based on symbolic simulation using our tool called Hydra. So actually, I think I have given you some motivation about why the simulation in hybrid system should be rigorous in many reasons. So maybe then another motivation of work can be presented this way. So many people are working on rigorous techniques for verification of hybrid systems, but we are working on rigorous simulation in contrast. So let me explain the difference between simulation and verification. So most research on hybrid systems aims at verification as decision problems. So so if you know what should be proved, then the verification will work well. So basically verification is a decision problem, and the decision problem is some problem algorithm which gives you the yes or no answer. So you will know that whether the system will work or not in the light of the specification. And if the system doesn't work, then most likely the decision problem will give you some counterexample. Okay. But maybe the rigorous simulation, maybe the power of rigorous simulation can be in some sense weaker. Maybe the verification procedure may be more expressive, and it has more powerful problem-solving techniques. But one good point about rigorous simulation is that it will require less from you and tell you more. I mean, so some verifiers are automatic, but some are just interactive. But in the case of simulation or model checking, you don't have to have no proof skills. So if the system is based on interactive self-improvement, then maybe the user should have quite good mathematical skills. But in the case of our systems, we require no proof skills. And the second point is that you don't even have to have the proof goals. And this means that maybe when you have some hybrid systems, maybe you don't even know what are the desirable property. So you are just interested in how it works and what properties it may have. So you can start using simulator even if you don't have any proof goals. So but still, because the simulation is rigorous, you can still see something, and the system can still be used to prove something. So actually, the simulator, a rigorous simulator, can be verified to use something. The most well-known example, which is not hybrid systems, but the well-known result about dynamical systems is that the existence of the Lorentz adapter was proved using the Warbeck-Tucker's rigorous simulator, and which won the Robert Moore Prize of the verified numerics in the year 2002. Also, the third point is that it will explain or give you the exposition of how it works. And so, as I demonstrated yesterday, it may give you some visualized trajectories if the system comes with some visualizer. And also, if the system is visualized, then you will be able to see how safe it is. So maybe you can get some a rough idea of how safe it is. So, okay. So actually, I gave you some demonstrations, but here let me explain the overview and features of the Hydro language. Okay. The first motivation is that maybe until several years ago, I was very new to hybrid systems, and I felt that the whole field of hybrid systems comes with many notations, concepts, and techniques, and I found it rather difficult for me or for my students to get into. Okay. So my challenge has been to see whether a rather simple or even simplistic formalism can address various aspects of hybrid systems. Maybe my framework may not be able to cover everything, so it may be rather weak for some purposes, but we hope that our formalism will cover reasonably broad class of hybrid systems. So the goal of the whole work is to identify computational mechanisms, and also to give you some tool or language for modeling and understanding systems that are not large but may exhibit a very subtle or problematic behavior. Because many of the hybrid systems have very delicate behavior. And the current non-goal is the modeling of large-scale systems, for which many other good numerical tools exist. So to be more specific, we are trying to have some declarative as opposed to procedural formalisms for hybrid systems. And the first motivation for me has been to minimize new concepts or notations which can be found in programming languages by employing rather popular mathematical or logical notations. So all these symbols are very popular. And so we try to use these symbols and try to give some computational interpretation to these symbols. Okay. And the second point is that I think we want to describe hybrid systems or dynamical systems as logical formula with hierarchy. Okay. So let me motivate the use of hierarchy in the next slides. But the thing is that unlike automata or hybrid automata, we don't have some explicit notion of state or state changes. We just use a logical formula with hierarchy. Okay. But still, so it looks very different from hybrid automata. But still, it turns out that the semantics. So this means that we use some mathematical symbols and logical formulas. So, but it is not just mathematics or logic, because it turns out that the semantics of the language comes with a large design space. So, for example, we allow the value of variables to have some uncertain values, like the variable x will be between 9 and 10 or something like that. So now given the two values, two variables, x and y, both of which may have some range of variables, then it is not clear how to compute these two uncertain values. Also, most hybrid systems, in most hybrid systems, the variables are mostly continuous. So maybe it is reasonable to assume that all variables in hybrid systems are piecewise continuous, and maybe piecewise differentiable. Okay. But so there is some discontinuity at some points. So it is mostly continuous, but not totally continuous. So to specifying hybrid systems, it is reasonable to have some assumption about the continuity of each variable. But it is not clear what continuity we should assume. So if, of course, we can explicitly state which variables are continuous at each time point. But then the description can be too complicated. So we decided to have some assumption about continuity, but how to give it was not very clear. And third point, which I stressed in the last talk, was that the whole system is constraint-based. So actually, we are giving some constraints. So equations or inequations over functions over time. And we use constraints, including ODEs, and we solve initial value problems. So maybe you can, so this is continuous variant of the programming over infinite list of streams, which are defined by difference equations. But the one strong reason why we stick to constraint-based approach is that it handles some partial or incomplete information properly. So, so many rigorous people are working on intervals. But so like x is between 1.0 and 3.5. But intervals can be interpreted as two inequalities. So x is larger or equal to 1.0, and x is less or equal to 3.5. So this can have some logical interpretation using inequalities. So they fit well within the constraint-based framework. Also, the constraint-based approach allows the modeling and simulation of some parametric hybrid systems. So even if we don't know the exact initial value of systems, we can perform some symbolic simulation of parametric hybrid systems. Okay. So the question is whether the whole, maybe the reasoning about constraints can be very complicated or not. Yeah. But at least theoretically, it is very simple. So because the only mechanism we use in the whole framework is the consistency checking of constraints. So, so we often check if this set of constraints is consistent, satisfiable or not. And sometimes we want to know if the set of constraints implies something. So if we know x equals 10, then let's suppose that in the subprogram, some rules say that if x is positive, then do something. Then we want to check if some set of constraints, including this equality, implies something. But this implication or entailment checking can be done as consistent checking by checking if x and not g is inconsistent or unsatisfiable. So this is valid only and only if this S and not G is inconsistent or unsatisfiable. So everything can be reduced to consistent checking. So I think the framework, the consistency gives you a very nice unified framework for the computation or computing over constraint systems. So the last point is about constant hierarchies. The idea is not very new. So actually, idea was first proposed by Alan Boring in the design and of some user interface systems in 1992, so 25 years ago. So the motivation is that we want to describe systems using maybe conjunction or disjunction constraints. But it is often very difficult to describe systems so that the set of constraints are consistent and well behaved. So suppose you have two variables, and so let's think about some linear set of equations, set of linear equations. So usually, if you have two linear equations, and two variables, then the values of variables are uniquely determined. But it is not always the case. Sometimes you have no solutions, and sometimes you have infinite many solutions. So, so even if you have very simple framework, it is not easy to ensure that the set of equations give you some unique answer. And so in general, it is even more difficult. So actually, we hoped that the constraint framework gives you a rather high-level framework for describing or modeling hybrid systems. We found that maybe the most important difficulty lies in the fact that even in our framework, it is not easy to write a model in such a way that the model gives you some unique solutions. So sometimes, often the models written by modelers or programmers are either over constraint or under constraint. So they tend to give us too many constraints or too few constraints. So, but it is a well-known fact in the field of artificial intelligence. Okay, so let me give you a very simple example of bouncing ball. So bouncing ball is a very typical physical phenomenon, and the ball normally obeys the law of gravity. So, but this is the default action, which is in effect maybe at most time, but it temporarily obeys the collision equation when it bounces on the floor. So this can be regarded as some exceptional framework. So if there's one flat floor, it's okay. But suppose that the ball is bouncing on some staircase. So there are many small pieces of floors in the staircase. So there are one default and many exceptions. So which means that we don't want to say that if the ball is not on this step and this step and this step, then maybe the default action, the description of the default action can be too long. So we want to say that this is the default and these are the exceptions. So this is a way when we represent knowledge in the AI framework. And it is known as some frame problem. Okay? And so as a frame problem, say that in the representations of knowledge for artificial intelligence, it is not possible to anticipate and enumerate all possible exceptions. So this is why the notion of default exists in many areas of computer science. So when you know about some object-oriented programming, maybe the class hierarchy are just about default and exceptions. Okay. So so I think we believe that something that addresses the default and exception issue should be included in the language. So and we want to define these issues as concisely as possible and in a modular manner. So these are the motivations. So this is an example of sawtooth function, and now maybe most of you know about these symbols. So this is the temporal logic operator saying that the derivative of f equals 1 holds at all non-negative time, and also f minus stands for the left-hand limit of f. Okay, and maybe I give you some demonstration of this program in which the value of the initial f, initial value of f is not known. So the program looks very similar, but because we don't perform a numeric simulation, but we do some symbolic simulation, we can still compute the set of trajectories. Okay. So the point is that the solution is the family of sawtooth functions with the slope 1 and the range between 0 and 1. So we don't know the value of f at a specific time point. So it can be anything, but we know that all trajectories have the slope 1 most of the time, okay, and oscillates. So if you want to verify that the trajectory oscillates and reaches the value 0.5 infinitely many times, then we can prove that even if we don't know the initial value of f. So let me introduce the second example, which is a very popular bouncing ball. So it is quite similar. Now we have the initial value and the initial velocity, and the parameters are constant here. Okay. So g is the gravity, and c is the coefficient of restitution, and this is the gravity law, and this is the bouncing law. Okay, so it's quite similar. So if the ball hits the ground, then the velocity will be set to minus 0.5 times the velocity just before the bouncing. Okay, so in this case, I will show you some demonstration soon. But let's observe that when the ball is not on the ground, so if the ball is falling, then or the rising, then all these four constraints are consistent. I mean, so this is a constraint just at time 0, and this is a global constraint, and this is the law of gravity, and when the ball is not on the ground, the height is not 0. So this is some conditional constraint, but its condition is false. So when the ball is not on the ground, this condition is the bounce condition is always satisfiable. Okay. So actually, we want to take as many constraints as possible, and actually, in this case, the set of four constraints is maximally consistent. But when the ball is on the ground, we want to forget about the four constraints, because on the floor, the speed of the ball cannot be differentiated. So and so sometimes we want to forget about the four constraints. Okay. So, but the basic principle is that we want to describe the system so that the system will give you some not over constraint and not under constraint systems. So the Hydra adopts the maximally consistent set of rules that respects the constraint priority. So there are no priority between this and this and this, but the priority exists between the fall and bounce. Okay. So this is the basic program. So let me give you. Okay.
So this means that init and param, they must always be.
Okay. So actually, I think that we take maximally consistent. So so in the initial semantics, we try to have a maximally consistent, even if these constraints are not weaker than anything else. But later we learned that the constraints at the top hierarchy should be enforced. And if you don't want to enforce these constraints, maybe you can have some empty or vacuous constraints, and under which you say that a constant A and constant B. So in this case, the program gives you So if A and B are not consistent, then AGI system will choose between A and B. I will give you some demonstration. Yeah.
What you represent on the graphic on the right, it is an envelope of...
This is the plot of the HT height. And this is the plot of the HT prime, the velocity.
You have a unique solution?
Yes.
So it computes, computes some kind of envelope, and here is it why it is thin.
Okay, so Hydra computes this trajectory symbolically.
Symbolically.
Yeah.
Why on the previous example,
Yeah.
I had the feeling that you have several solutions.
Okay, so even in this case, the Hydra gives you some symbolic solution. So the family of solutions has actually the solution has, okay, in this case, the value of f is not totally known. But in this case, our implementation first create a fresh parameter whose value is not known, but whose value is between 0 and 1. And the trajectory is just parameterized using that parameter. Okay. So I'll give you some demonstration. So it's much better. Okay. So now the ball is always okay. So yeah. Like right. Yeah, so now the ball is moving in this way. Like with, maybe this is more clear. So yeah, actually, so there can be very small variations. The one is that because we know that the speed is not continuous, but the height of the ball is continuous. So maybe we can omit this minus, which is the left limit of y. And we can change the program slightly, and let me try. And it still works. And also, maybe the horizontal axis need not be the time axis. So we can change the horizontal axis to the velocity. Then it's something like that. Okay, maybe okay. So this is a sort of the phase space of the bouncing ball. Okay, and you can increase the number of phases to maybe 30 or something. Then so now the left axis, the horizontal axis, the speed, and the vertical axis, the speed, the position of the ball. Now the system cannot reach the simulation up to the 0 point. But if you have time, then you can see that the position of the ball just reaches the origin of this coordinate. Okay. So let me show you some internals. So in this simulation, it's like this. So the system, actually the system tries to solve the set of equations for each phase. And the phase means that first the system tries to solve the set of equations for time 0. And then after that, the system solves the set of ODEs and find out when the next bouncing will happen. So actually point phase means the solving of the initial state, and the interval phase, IP, means the solution at the first flying phase. And the PP3, point phase 3, means that the first bouncing. And IP4 means that the ball is rising and falling. So so all solutions are given in the symbolic form. So this means that the system does not scale for some complicated systems, but it works well for reasonably small systems. So in this case, the actually, so unless we tell something to the solver, the system sticks to some rigorous solution. So maybe the numbers can be quite large. And then let me give you some example of parametric hybrid systems. So let's say that the value of 5 is between 5 and 15 or something. Then we can still prove something. So it's better to show you this trajectory, and then you can see this set of many trajectories. So this means that the solution was obtained by a single computation, but using the parameter p. But after that, to visualize the trajectories, we assign various values to the parametric solution of the bouncing ball problem. Also, yesterday, the Professor Moji gave me some question about uncertainties, and so I will show you another example here. Okay, so this is the sawtooth wave with 2 different slopes. So if you don't know, so in this case, the sawtooth function has 2 choices. One choice is to set that slope to 1, and another choice is to set that slope to 2. Okay, and the drop condition is the same. So then, by giving this program, the system chooses between increase and increase 2. So this and this are not compatible with each other, but the system tries to choose this or this in a non-deterministic way. So let me give you some symbolic solution for this. So actually, this is very expensive, so let me stop the simulation and go back. And okay. So actually, this is a symbolic simulation. So, and using the standard mode, the system will choose one of them. But if you specify the system will do some non-deterministic search, then system will give you, in this case, how many solutions? Okay, so there are many phases, and in this case, system computed 32 cases. And so let me just review some cases. For example, the case 21, the system chooses this slope 2 between time 0 and 5. And in the next, sorry, maybe it's better to just put the result into some file, and so in this case, the first case, the system chooses the slope 2 for the first rising, and then again this slope 2, and then again slope 2. It's okay. Sorry. Yeah. I will. Yes. Yes. Slope 2 here. So you just please look into the slope of the interval phase, and slope 2, and okay.
So you
yeah.
stick to the same slope until
Yeah.
it drops, or
Yeah. Yeah. Okay. And then, but the another solution give another. In this case, it started with slope 2 and slope 2, and then. Well, so all slope 2, maybe. But in this case, yes, slope 1 is chosen. Yeah. So actually, yeah, in this, what I want to say is that in this program, maybe there are 2 choices at each phase. I mean, so at first rising, there are 2 choices, and when the trajectory drops, then the choice is made. Another choice is made. So in this case, maybe some exponentially many choices are made during simulation. So we have to be very careful, because unless we specify the system very carefully, then there can be so many different choices in our simulation. Okay. So also, I mean that, but this is give you a very important observation that so this is something like either f prime is 1 or 2. Yeah. So we don't know the value of f prime at each time. But this is very different from either f is always 1 or f prime is always 2. And this is much more restricted, and this is much more free. In this particular case, the system succeeded in simulating the first specification. Yeah, but this is very related to the computability issue of the hybrid systems. Okay, so let me get back to the some other issues. But so now I explained how to represent constraint hierarchy. But the language comes with some sublanguage which allows you to express the hierarchy between different constraints. But internally, these hierarchies are expanded to the partially ordered set of the set of constraints. Okay. Yes, 5 minutes. Okay. Yes. So in this case, internally, given this specification, we have a hierarchy between this set of constraints and this set of constraints. So okay, and so I think it's better not to get into the details of the syntax semantics, but this is a basic syntax. Yeah, with the program is a set of rules and set of definitions which combines, which specifies how to combine the set of rules. And and the rule set is the partially ordered set whose elements are set of rules. And definitions is some name followed by some set of constraints, some constraints. So actually, each rule is a function from the rule name to constraints. And these are typical constraints. And it's atomic or conjunction or implication or some universal always constraint. And this existence constraint has not been implemented, but we plan to implement in the near future. Okay. And guard is atomic or conjunction, or I think we now allow them disjunction. And each atomic constraint is an expression, two expressions connected by some relational operator. And in expression, we allow the derivative, prime notation, and we allow some previous notation. And I think we have not much time to get into detail of the semantics, but in this talk, I will give you the overview of the semantics. Actually, so usually when we design the programming language, we start with operational semantics. It is, and then we think about the denotational semantics to justify everything else. But in this particular language, we started with a sort of the declarative semantics. Yeah, so that so we can we study what trajectories a Hydra program denotes. So I think this is the first thing we considered about this Hydra language, and then we designed the operational semantics or the execution programs. So which states how to compute trajectories of a given Hydra program. So this is unlike many other languages because of the two reasons. One is reason that we well know from the very beginning that the completeness of the operational semantics cannot be expected because of the very negative result of the reachability problem of the hybrid systems of 20 years ago. And also, this is not a program language, but it is a modeling language. So we anticipate that quite a different execution method should be expected. So sometimes we do some symbolic technique, and sometimes we do some numeric technique, and sometimes we want to run the program backwards from the goal state, and sometimes we want to compute the invariant so that we can analyze the systems with some zero point or systems with some sliding mode. So and actually we are currently working on how to simulate some hybrid systems with some sliding mode or chattering behavior. So I think it's time to stop and have a short break. Okay. Yes.
You said it's a modeling language.
Yeah.
So, except the graph part, what else the programmer, the user gets out of the program?
Sorry,
out of the program.
Yeah.
So, the modeling aspects, like whether he can also view the program as a more of a graphical view.
Yeah.
Maybe a state chart or something like that is possible.
Okay, graphical view of the program itself, and not the project tree. Oh, that's a good question. Actually, there is some. There can be static view. But what we have implemented experimentally is that sometimes we can construct hybrid automata from this specification when we find some recurring looping behavior. So that's will give you some graphical representation. And for more static graphical representation, I'm not sure. So maybe, but there is one graphical view of the system. Okay, which is about the dependency of constraints. Because in complex systems, there are many variables. And this constraint mentions this and this variable, and this condition mentions this and this variable. So some conditions are independent of each other. And then these conditions can be solved independently. And we don't want to recompute some constraints after something happens. So internally, we have a graphical representation of constraints to maintain the dependency of constraints. And I think that information will give you some clue about how complicated the system is. Okay.